9s and welcome to WorksheetCloud Maths. I hope you're all well today and you're looking forward to today's lesson as much as I am. But let's get going. Today we are going to look at the geometry of three-dimensional shapes, so 3D shapes. And I hope it's quite an exciting lesson for you. For those of you who are joining us for the first time, I hope you are going to enjoy this lesson so much that you are going to continue to watch our maths lessons. So welcome to you. Right, let's get going with today's lesson. Okay, so first of all, we're going to look at terminology relating to the geometry of 3D shapes. This may be new to you, but you may have touched on this last year in grade 8. Let's have a look. So three-dimensional objects include right prisms, pyramids, and platonic solids. So let's go through what those actually mean. Okay, so first of all, polyhedra, which is the plural for polyhedron, have flat sides or faces which are all polygons. Again, we'll go through that in more detail later on. A right prism has two parallel congruent faces called bases, which are polygons, and lateral faces, which are rectangles. Again, we'll go through that just now with looking at an example. So just to go over it again, a right prism has two parallel congruent faces called bases, which are polygons, and lateral faces, which are always rectangles. All right, a pyramid, as you know, has a single base, which is a polygon, and sides, which are triangles, which meet at a common vertex. Okay, so you can picture that because you all know what a pyramid looks like. And then a platonic solid has faces which are congruent, regular polygons. In other words, all the faces are exactly the same. Okay, so let's have a look at a right prism that has two parallel congruent faces called bases, and they are polygons, and then they have lateral faces which are always rectangles. So there's an example of a right prism. As you can see here, there's the congruent face and a congruent face which are parallel, and those are the bases. And as you can see here, these meet at right angles, so that means it's a right prism. And all the other faces, the lateral faces, are all rectangles. So let's label it. There are the lateral faces, which are rectangles. So that's the faces that go next to one another and that make up the 3D part of the shape. In other words, they connect the bases. Okay, and there are your two congruent bases. So your bases are exactly the same, and your rectangles therefore will be also the same size and the same shape because they are congruent. Okay, so again, here are your lateral faces. There's a lateral face over there. Here's another one in the front, another one there, and the one at the back. Those are all lateral faces and they are all rectangles. Then you have your two bases which are congruent, so they will always be the same size and shape, and in this case it's a pentagon. But it could also be a triangle, which will create a triangular prism, or it could be a square, which will create a cuboid or a cube, or we could call it a rectangular prism. It could be any shape. It could be an octagon. The bases could be octagons, so therefore it would be an octagonal prism. Right, but they are all right prisms because where the congruent bases meet the lateral sides, it forms a right angle. Right, the next one, which is a pyramid, it has a single base, which is a polygon, and it doesn't always have to be a flat base. In other words, it is a flat base. It doesn't always have to be a square. It can be a rectangle, it can be an octagon, whatever. It is a polygon, and it is the single base at the bottom, and then the rest are made up of triangles. The triangles make up your lateral sides, and those triangles meet at a common vertex. So if we have a look here, there we have a pyramid, and as you can see here, it's a hexagonal base. So that forms the base, and it's one base, and then all the triangular sides meet together at one common vertex. So there's your triangular faces, which are also polygons. There's your single base, which in this case is a hexagon, and there is a vertex. That is the common vertex that they all meet at. These down here are also vertices, but they are not the common one where all the triangles meet together. Right, the last one, a platonic solid has faces which are congruent regular polygons. So there we go. That is a platonic solid. All the shapes are exactly the same. So they're the same size and the same shape. And in this case, we could either call this a tetrahedron or we could call this a triangular-based pyramid. And as you can see, because it is a pyramid, they all meet at a common vertex in this case. And they are all the same triangles, even the base. So it means that they are a platonic solid is made up of congruent regular polygons. Right, there you can see the vertices, and there you can see the triangular faces. Okay, these are polyhedra that fall into there are polyhedra that fall into more than one of the three categories. So i.e. right prisms, pyramids, and platonic solids. As you saw in the last one, platonic solid that we looked at was also a triangular-based pyramid. All right, so that one fell into more than one of those three categories. Okay, so we can look at two new formula here to do with the geometry of 3D shapes. And the one formula is relating to the number of faces, the number of vertices, and the number of edges. And that means in a polyhedron, this is the formula. It's faces plus vertices minus edges equals 2. So if one of those are missing, we can always work out using our knowledge of algebra what the value is of the missing number. Okay, and this is known as Eulers Law. Now some people say that differently, but I just say Eulers Law. Okay, so that is Eulers Law. It's F faces plus V vertices minus the edges is equal to 2. And we will work with that a little bit just now. The next formula is angles in regular polygons. So there's a formula to work that out. And the sum of the interior angles of any polygon is n minus 2 times 180. Each interior angle in a regular polygon, we'll go over the n side just now, polygon therefore measures n minus 2 times 180 over n. And I'll explain a little bit more on that later. Okay, so using Euler's law, here we have it. Remember, faces plus vertices minus edges equals 2. So if we look at the following shape, there we have a table with different shapes in, and in each case we are missing a few things. So we would be able to then work out what these missing components are. So let's look at each one individually. Here we have that shape. Okay, we know that it is a right prism. Why? Because there are rectangles that meet two bases, two congruent bases, and where the rectangles meet, the rectangles are, they have right angles, sorry. Okay, so first of all, we're going to name this shape, and because it is a prism, it's a right prism, we look at the bases and we name it according to the bases. So this would be known as a triangular prism. Okay, we also know that it has 5 faces, so that we can count to check. That's one on the other side, another one there. So we've got 3 rectangles and 2 bases, so we've got 5 faces. How many edges do we have? Well, let's count. We've got 3 in this base, 3 in that base, which makes 6, 7, 8, 9, where the rectangles meet. Okay, so we've got 9 edges and 5 faces. So we can use Euler's law to actually work out how many vertices we got. So let's try and do that right now. Okay, so there we have our formula, which is up here to remind us, and we plug in what we know. So we know the number of faces, we know the number of edges, but we don't know the number of vertices. And we know that faces plus vertices minus edges gives me 2. Faces are 5 plus the unknown minus 9 is equal to 2. Let's use our algebraic knowledge and figure out what V is equal to. So the first thing, take your 9 across the equal sign. 2 plus 9 would give me 11. So 5 plus whatever vertices there are is going to give me 11, like that. Okay, again, we can move the 5 across the equal sign so that we are left with V on its own. So V will be equal to 11 minus 5, and 11 minus 5 we know is 6. Now we can double check that because these are the vertices, remember, where the sides meet. 1, 2, 3, 4, 5, 6. So Euler's law definitely does work. So the number of vertices we have in this shape, in this 3D shape, is 6. And remember, this we know is a right prism because it is made up of sides, lateral sides that are rectangles, and then two congruent bases, which in this case are triangles. Okay, let's look at this one. Again, we've got to name this shape, and now we've got to work out how many edges there are. So let's have a look what we do. This shape is definitely a pyramid. It has triangular sides that meet at one vertex, and it has a base as being a square. So we could call it a square pyramid. Okay, we could also call it a square-based pyramid, but square pyramid is fine. It means that the base is square, and we know that a pyramid meets at one common vertex. Okay, we now can take Euler's law and then substitute in what we know to find out what we don't know, and in this case we don't know how many edges there are. So there's our formula. Let's substitute into the formula. We've got the number of faces, which is 5, the number of vertices is 5, and let's just double check that before we plug them in. Okay, number of faces, you've got one square base and 4 triangular faces, lateral faces. So that gives me 5 faces. Let's work out the vertices. We've got 1, 2, 3 at the back there, 4, and 1 at the top gives me 5. So let's substitute in. We've got 5 plus 5 minus E is equal to 2. 5 plus 5 is 10, minus E is equal to 2. So let's take the E across to make it a positive E, and the 2 back across the equal sign. So it's going to be 10 minus 2 is equal to E. 10 minus 2 is 8. So there are 8 edges. Let's double check and let's count. 1, 2, 3, 4, and 4 of the base. So yes, there are 8 edges. So there we go. Now guys, these shapes that we are working with are pretty easy to actually double check the number of edges or vertices or faces. Sometimes you get very detailed, very complex, let me put it that way, shapes, and it's not always easy to count all the vertices, all the edges, and all the faces, and that's why we have the formula that we can use to work out. Right, let's look at the last shape. That shape, what do we call that shape? And we have our vertices and our edges, and we need to know the number of faces. So that is a rectangular prism. Remember, it's got rectangles as lateral faces and 2 congruent bases, which are also rectangles. We've got our vertices and our edges, so we can use Euler's law to actually work out how many faces we've got in this one. Okay, number of faces plus vertices is 8, minus 12 as the edges gives me 2. So we've got 8 minus 12 is equal to 2, and there we take the 12 across, so we go 2 plus 12, which will give me 14, and we've got 8 on the other side, which means we can still say 14 minus 8. So there we've added our 2 plus our 12, gives me 14. Take the 8 across, we've got F is equal to 14 minus 8, and we all know that that will give us 6. So we have 6 faces. Let's double check before we fill it in. 1, 2, 3, 4, and the top one and the bottom one gives me 6. All right, so we know definitely that Euler's law definitely works, and we can now apply that to any shape as long as we know some of the faces, either the faces, the vertices, or the edges, and then we can work out an unknown. Okay, calculating angles in regular polygons. As I said, we will go over this when we looked at it earlier. I said we would go over it again. So to calculate the sum of interior angles, we use the formula n minus 2 times 180, where n represents the number of sides. So that's why I said to you earlier, we will look at what n is, and n is the number of sides in your polygon. So the number of sides minus 2 times 180 degrees gives us the sum of the interior angles. If we want to find each interior angle, we are then going to take that formula and divide the whole thing by the number of sides. Okay, so again, n is the number of sides, so whatever the polygon that number of sides minus 2 then times 180 will give you all the angles, all the interior angles in your polygon. But if you want each angle, then obviously you are going to divide that whole lot by the number of sides. So let's put this into action. Okay, calculate the size of each interior angle in a regular octagon. So there's the octagon. As we know, an octagon is an 8-sided polygon. So there, when we substitute in, wherever n is, it will be 8. So it will be 8 minus 2 times 180, all divided by 8. So there we have it. So what is 8 minus 2? Obviously, we know that that is 6. So 6 times 180 divided by 8 still, because we still got 8 sides to this octagon. 6 times 180 is 1,800. Okay, so 1,080 degrees. So the sum of the interior angles in an octagon is 1,080 degrees, and then we divide by 8 to find out each interior angle. And each interior angle in an octagon is 135 degrees. Okay, you all see that? You don't have to remember this off by heart, because you can always work it out using this formula. So you must remember the formula, but you can always then calculate the sum of all the interior angles, and then when you divide that by the number of sides, you get each interior angle. So all the interior angles together of the octagon is 1,080, but each one separately will be 135. Let's have a look at another one. Now we need to calculate the size of each interior angle in a regular pentagon. And there we have our regular pentagon. So we all know that a pentagon has 5 sides. So where we substituted in 8 in the octagon, we are now going to substitute in 5. So n minus 2 times 180, all divided by n, where n is going to be 5. So it will be 5 minus 2 times 180, all divided by 5. 5 minus 2 we know is 3. So 3 times 180 divided by 5, that gives me 540. Now remember, the 540 is the sum of all the interior angles, and then we're going to divide that by 5, and that's going to give me 108 degrees. So each angle in a pentagon is 108 degrees. Once again, we don't have to commit that to memory, because if we know our formula to work it out, then it will be easy. Okay, right. Now there is a short way of describing a regular polyhedron. We don't often see this, but this is just something interesting to know. Okay, so we use 5 numbers in order to do this. Okay, so the first one is the number of edges in a face, and we'll go over this just now, but look at one face and determine the number of edges in that face. And remember, it's a regular polyhedron, which means that all the faces are going to be exactly the same. So the number of edges in a face, then we're going to look at the number of faces that meet at a vertex. Then we're going to look at the number of faces altogether in this polyhedron. And then we're going to look at the number of vertices that the polyhedron has, and we're going to look at the number of edges. So that then gives us a way of describing a regular polyhedron. And it will be a whole list of numbers, but we can go back and then we can look at what each number represents, and then probably put the polyhedron together. So, for example, a tetrahedron or a triangular pyramid, there we have it there. So we first are going to look at the number of edges in a face. In one face here, it's 1, 2, 3. So our first number will be 3. Then we have a look at the faces at a vertex. So that's a vertex. How many faces? It would be this one, and the back one. Okay, the lateral faces. So that will also be 3. The number of faces altogether will be 4, because now we're including the base. The number of vertices will be 1, 2, 3, 4. And the number of edges will be 1, 2, 3, 4, 5, 6. So let's see if that worked out. There we have it. Number of edges in a face is 3. Remember, one face. There's 1, 2, 3 edges in the face. Then we had to look at the number of faces that meets at a vertex, and we decided that was 3. Then we looked at the number of faces altogether in the polyhedron. That was 4. The number of vertices was also 4, and the number of edges was 6. So let's have a look here at, there we have the little formula in the, or the structure in the corner there, and we can refer to that. Let's look at that shape. Okay, first of all, we're going to look at the number of edges in one face, and we can tell that the number of edges in one face is 4. So our first number will be 4. Then we look at the number of faces at a vertex. So here's a vertex, there's that face, that face, that face, meeting at that vertex, so that will be 3. So far we've got 4 and 3. Then we look at the number of faces in the whole shape, and that will be 1, 2, 3, 4, plus the 2 bases, that will give me 6. The number of vertices altogether will be 8, because I've got 1 there, 2, 3, 4, 5, 6, 7, 8. And then the number of edges altogether will give me 4 on this side, 4 on that side, and another 1, 2, 3, 4, which actually gives me 12. So that is a cube, and the short way of writing a cube in this sequence will be 4, 3, 6, 8, and 12. Okay. The next shape we're going to look at is that one. What do we call that shape? It's an octahedron. Why? Because it has actually got 8 faces that are congruent. So this one is made up of 8 triangles that are all exactly the same. So now we're going to look at the number of edges in a face. We know that it's made up of triangles, so that must be 3. Then we look at the number of faces at a vertex. Okay, here we got 4 faces at each vertex. If we look at this vertex here, 1, 2, 3, 4 faces are meeting there, but at any vertex in that shape there will be 4 faces. Then the number of faces altogether, we know because it's an octahedron, there are 8 faces. The number of vertices altogether will be 1, 2, 3, 4, 5, 6, and then the number of edges altogether will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So do we get that? Yes. 3, 4, 8, 6, and 12. And remember, it's 3 edges on each face. It's 4 faces that meet at each vertex. It's 8 faces altogether. It's 6 vertices altogether. And then it is 12 edges altogether. So that's just a short way of describing a shape. Like I said, you don't really come across this too often, but it is just interesting to know. And if you do know the way of describing the shape, you can quite easily name it. Or if you've got this structure, you can probably quite easily draw it. Okay, right guys, that was today's lesson. Thank you so much for listening. And as I said, those of you that joined us for the first time today, I sincerely hope that we are going to see each other again sometime. Right guys, keep well until the next lesson. Bye-bye for now.